Okay, so somehow some of the videos got cut or messed up or whatever. So I wanted to make sure you have these slides here, which is about 19 through 39, I think is what you're missing. So SN2 mechanisms. SN2, bimolecular, bi meaning two, molecular, your molecules, react at the same time. And this is in the rate determining step. Because of this, there's an inversion. So let me show you this. There's a lot going on in this slide, so let me show you this step by step. Okay, so first of all, S, S stands for substitution in nucleophilic 2, meaning two things are going to happen at the same time, meaning bimolecular. So what you're going to be looking for, first of all, it's a substitution. So let me just show you the product. So when you're predicting the product, the OH is going to substitute in for chlorine. Like that. Okay, see the substitution? So it's a pretty easy product to predict. You just switch the leaving group in the nucleophile. Okay, now let me show you the mechanism here. You have your electrons here. It's going to make a bond right here at this carbon. The reason is there's an electronegative carbon. Okay, so there's a partial negative, which creates a partial positive right here on this carbon, because the chlorine is pulling the electrons away from carbon because it has a stronger attraction to them. So there's less electrons around carbon because they're being pulled closer to chlorine. So because of this, this negative charge nucleophile wants to come in and make a bond there. Which, put my electrons here. Now if I do this, carbon will have too many bonds to it. There's hidden hydrogens here. There's, if I draw them here, 1, 2 hidden hydrogens there. So I can't just make 4 or 5 bonds to carbon. It can only have 4. So chlorine is going to leave and take these electrons with it, and OH is going to attack, giving us this product here. Now, the inversion. You see there's a lot of things going on here at a time, okay? So because of that, the OH is going to come in the opposite side of chlorine. Notice I have it coming in from the bottom, like chlorine's on top. Again, there's a lot of things going on. There's not a lot of space. So they come in opposite of each other. So if I was doing the stereochemistry, okay, now this doesn't have a stereocenter, but let's say it did. If this was an R, that means it would invert to an S because it would come in opposite. Okay, so when you're doing your products, so if you have one that's secondary, let's say your chlorine right here, the living groups are here, your OH would come in from the bottom, and so when you're redrawing this, you would actually draw it OH now here on the opposite side, okay? The other thing is these prefer primary carbons. And again, it has to do with steric hindrance. Steric hindrance is just a fancy word meaning crowded, okay? It can go secondary, like right here. This is a secondary carbon, but it's a lot slower, and it's going to start competing with like SN1, E1, E2. So preferably it wants primary carbons. So if you have a primary carbon and a good nucleophile, then more than likely it's going to be SN2. Here's the energy diagram as I was kind of talking about here. So here is the starting material, and you see at the transition state here, this is the rate determining step. Let me maximize this a little bit more. Here, as OH is bonding to it, I, in this case is your leaving group, is leaving, okay? So that's why it shows the dotted line, because they're both happening at the same time as I is leaving. It hasn't quite left yet, so it's a dotted line. OH is forming. It hasn't quite formed yet. Okay, so the transition state, they says the highest energy here, which is right there. So the transition state for this mechanism is, again, as OH is starting to form the bond and the iodine, your leaving group, is starting to leave. Your leaving group, your best leaving groups are going to be pretty much any of your halogens. Fluorine's not a good one because it's actually a weak acid. Anyway, but long story short, most of your halogens are going to be good leaving groups. That's what you're going to be seeing. A lot of chlorine, bromine, and iodine mainly. Here are the nucleophiles used for SN2 reactions, I minus. That's a really good nucleophile. And what's nice about iodine is that it's not a very good base. So the difference between a nucleophile and a base, that's important. So a base takes off a hydrogen. That is its job, if you want. A nucleophile makes a bond to carbon. So they're similar because they both, a base can be a nucleophile and a nucleophile can be a base. Okay, so think about like yourself. You know, like me, for example, I am a professor, but I'm also a mom, I'm also a wife, I'm also a sister, and so forth. You know, I have different roles and I play them different depending on which one I am. So, you know, when I'm being a mom, I act different than if I'm being a wife, for example, okay? But yet, it's still me. So you can be a base and a nucleophile, okay? But just because you're base doesn't mean you're a nucleophile, and just because you're a nucleophile doesn't mean you're a base. So iodine's a good one because it's a really good nucleophile, but it's a really bad base. So it's a good one so you don't have any competing reactions, because you might think, okay, well, if I put hydroxide in there, because hydroxide is a good base and a good nucleophile, well, you know, is it going to act as a base or a nucleophile? Which one? How do I know? Well, that's the problem, is there are competing reactions, and so you're going to get kind of a mix. Now, there's things you can do that can ensure that you get more substitution versus elimination. Um, so yeah, keep that in mind. So you can change the solvent, um, which is basically what everything's mixed in, and we'll go over some solvents here in a minute. You can change the leaving group. You can heat it up or cool it down. There's things you can do, conditions that'll make one favorable over the other to give you more of the product you want, for example. So the ones you're going to see more often, I would say iodine, okay, as a base nucleophile, or not just a nucleophile. Hydroxide, OR is a good one. R is just your carbon group, so basically oxygen as a nucleophile or a base. Sulfur is a good one there, SH, because that is a good nucleophile, but not the best base. Anyway, so those are some good nucleophiles to use there. So here, as I was saying, these are going to be your strongest ones. Notice they all have negative charges. Yeah. This is basically what I was going over for. Strong bases are also strong nucleophiles typically, but not all strong nucleophiles are basic. Anyway, so you'll see these. I would say the most common one you're going to see is going to be like OH, OR, in most of your reactions you'll see. So again, this is where I was telling you the difference between a base and a nucleophile. A base takes off a hydrogen because that's what it's attracted to. It's attracted to hydrogen. It wants a hydrogen. An acid, its role in life is to give up a hydrogen, so it reacts with a acid, takes off a hydrogen. A nucleophile, on the other hand, makes a bond to carbon. So that's the difference between a base and a nucleophile. Here are trends in nucleophile. A negative charged nucleophile is stronger than its neutral counterpart. So like hydroxide versus water, sulfide versus hydrogen sulfur, Anyway, so the negative is stronger because it's more reactive. It has a negative charge and doesn't want to. So it wants to neutralize itself versus if it's already neutral. Nucleophiles decreased from left to right. So on the periodic table, the further left you go, the more nucleophilic. Now we're not going too far left, so don't go all the way over to like hydrogen or something. But looking at like nitrogen, oxygen, and your halogens. Okay. Oops. Here we are. Going down, they increase going down because of the size of it. Now let me show you why this is. Okay, so iodine, this is the one I was talking about. So even though iodine is pretty far to the right, it still, since going down on the periodic table, it makes it a very strong nucleophile. So let me show you this trend here. Get rid of these. Okay, so here's my periodic table. Something like that, pretty close. So going down, it gets stronger. Going to the right, it gets stronger nucleophile. Now bases are a little bit different. Going to the left, they are stronger, but going up makes a stronger base. So that's why going down, you could have, like I was talking about iodine, it's a stronger nucleophile, but not a very good base. Going up makes a better base. Now here's what happened. Iodine is very big. It has a lot of electrons around it, okay? Now only the outer electrons are used for bonding to like a carbon, for example, okay? Now you have, protons and neutrons in here. The most important part is protons. Now the further away you are from the nucleus, the easier these electrons are used to bond. So if I'm looking at fluorine, for example, okay, it's not very big. And so these electrons are closer to the nucleus, and the nucleus doesn't want to give these electrons up, okay? It loves its electrons, and it's really close. So think about a magnet. The closer you put a magnet to another magnet, if they're attracted to each other, the harder it is to pull it away, right? But the further away you have the magnets, the less attraction there is. And so that's why going down the periodic table is a stronger nucleophile, because the electrons are further away, so they're easier to use for bonding because they're not held as strong to the nucleus there. And so this is basically what I just showed you here. The bigger atoms have a softer shell, which can start to overlap the carbon from a further distance. So like I said, they're larger. The electrons are further away from the nucleus, so they're easier to bond with something else because they're not held as tight. Here's a solvent effect, okay? Polar protic solvents have acidic hydrogens. So we're really looking at OH and NH, which can solvate the nucleophile, reducing their nucleophilicity. Okay, so the nucleophilicity in protic solvents increases as the size of the atom increases. So basically what happens is a polar protic solvent stabilizes your reaction, if you want. It stabilizes charges. So it can make your nucleophile not as reactive. So like for example, a SN2 reaction, you're not going to want a polar protic solvent because it's going to stabilize the reaction. You want it to react, okay? Now there's times where you do want to stabilize things, but this is not one of them. You want your nucleophile to be really strong and reactive, so you don't want to stabilize it. So polar protic solvents aren't good for that. So there are aprotic. They don't have acidic hydrogens, so they cannot stabilize anything. But it's a really good medium to mix, your two reactive substances together, because basically it doesn't affect anything. So they're aprotic, so you'll see like DMF, DMSO, acetone, acetonitrile. I would say DMSO is one of the most common ones used. So basically it's not going to interact with your reaction at all, which is what you want. Is you want it to make it reactive. You don't want it to stabilize anything. Now we'll see an SN1 reaction, there are, you do want to stabilize that because you're going to form what's called a carbocation. So you want it to be stabilized. Plus, a lot of times your solvent is also your nucleophile, and it's very common to have that for SN1. So SN1, like or I should say one reactions, like E1, SN1, you're going to use your protic solvents. For SN2, E2, you're going to use your aprotic solvents. Leaving group. You want something that's not going to be that reactive whenever it leaves, because you don't want it to compete. You don't want it, so for example, when I had chlorine as a leaving group, you don't want it to compete and try to knock, OH hydroxide off again. So your halogens right here, like I said, chlorine, bromine, iodine, these are your best leaving groups because they're actually, even though they might have a negative charge, they're pretty stable on their own. The other ones, what you notice here, these have double bond oxygen, so they have resonance, so they can stabilize. So your sulfurs and phosphorus groups. Also, something that's neutral, like water and alcohols, as it leaves. So when it's on, it's going to have a positive charge. When it leaves, it'll have a neutral charge. So these are good leaving groups. Everything needs a good leaving group. So your SN1, SN2, all of those would want a strong leaving group. But here's what I was talking about the structure. So here, the reactivity, you would want a methyl group, which is it's a special primary. A primary, secondary, and it won't go at all with a tertiary. And again, this is due to steric hindrance, so which is, again, a fancy word for being crowded. So SN2, you really ideally want primary, and you could do a little bit with secondary. But with secondary, you're going to get a lot of competing reactions, like with some eliminations, some SN1 in there. So primary is ideal for SN2. And this is just showing again, it's just, you get sterically hindered. It gets too crowded. If there's too many carbons in there blocking the way, then your nucleophile can't get in there. Stereochemistry, so here's Walden inversion. This is what I was talking about too with the mechanism. You see how the OH comes in from the back, and your bromine, your leaving group, is going to leave from the front or the top, basically the opposite. 180 degrees from each other. So your leaving group could be, if your leaving group is at the top, this is going to come in at the bottom. If your leaving group is on a wedge, it'll come in on a dash. So it's always the opposite. Okay? Here's your transition state where they're both like forming and leaving. And then you see here, now your OH is on the opposite side. So you see here, it starts as an S and inverts to an R. Now you're only going to see this with your secondary carbons, because if you're primary, you're not going to have a stereocenter. But it'll still come in from the opposite side, you just won't have an enantiomer. But if you do have an enantiomer, so if you have an SN2 reaction that is secondary, you will see an inversion of stereocenters every single time, 100%. And so that's everything for SN2. Now here's SN1. SN1 is pretty much the opposite. It's unimolecular, so only one thing will happen at a time. It's a two-step mechanism, because remember before with SN2, everything happened together. Two things happened at one time. The rate is first order in the alkyl halide and zero order in the nucleophile. So basically the rate determining step is your leaving group leaving. So it doesn't need a strong nucleophile to come in. So that's why you could use a protic solvent, because you might think, okay, well, SN1 also uses a nucleophile. Why would you use a protic solvent versus an aprotic? Because wouldn't you still want a strong nucleophile? Well, the rate determining step is just the leaving group leaving, not the nucleophile coming in and attacking it. So you want to stabilize that leaving group leaving, which it needs a very strong protic solvent. A racemic mixture occurs, okay? Because you form a carbocation, and I'll show you this. A carbocation is planar, meaning it's flat. So there's not steric hindrance as you would have before. So your nucleophile, when it does come in, is after leaving group has left. It can come in from the top or the bottom. It doesn't matter. There's not that much of a preference. Maybe a little bit slightly away from the leaving group, but nothing. It's pretty much a 50-50 mixture. So here, let me draw out the mechanism. This is what it's trying to show you here. Okay, so here's SN1. Now, this is a substitution, okay? And the final product will be substituting this, your nucleophile for the leaving group. Now you're going to have one hydrogen less, okay? So SO1 tends to have either an acidic or a neutral nucleophile, okay? Because remember, nucleophile doesn't matter. It doesn't have to be a strong nucleophile. It's actually better if it's not, because then you can do, it won't make any SN2s. Anyway, basically what happens is now you get this, and you'll find hydrochloric acid. It'll take off on your hydrogens. So the what things you want to notice here. First of all, you see this carbon here? This is a tertiary carbon. SN1 is going to prefer tertiary carbons for this reason. First of all, your leaving group will just leave on its own. Now before, with an SN2, I had to have the nucleophile attack, which forced the leaving group to leave, basically. In this case, you're going to have your protic solvent, say water in here, okay? Notice that a lot of times your solvent and your nucleophile will be exactly the same. That's very common for SN1, okay? So water will come in and is going to kind of stabilize this reaction. And this is what's going to happen. Now, you're going to have this positive charge right here. Chlorine leaves as your leaving group. Right here. Okay, and I could put the lone pairs on here too. It's going to take both of these electrons from this bond and leave. Okay, since it took both electrons there, it's going to leave carbon with a positive charge, which is a carbocation. Always. These are always the steps of SN1, always. Okay, so now you have this positive charge. So you see here, this is what needs to be stabilized. So when you have a polar protic solvent, think of this as a charge stabilizing solvent. So this will stabilize this positive charge to ensure that it forms, okay? Because it's not that easy to just make a leaving group leave on its own. But if you have a solvent in there that can stabilize it, and you kind of heat the reaction up a little bit, it'll do it. Okay, and notice you need a very stable carbocation. The more carbons it has off of here, the more stable. This is because carbons have electrons around it. Okay, what charges electrons? Negative. So again, it stabilizes this positive charge. Now, if I had less carbons around it, I would have less electrons to stabilize it. Now, it's kind of a minor stabilizing effect, but it still is a stabilizing effect. So it will always prefer a tertiary, then a secondary, and then primary. Pretty much it won't go primary because there's not anything to really stabilize that. So again, you need to stabilize the carbocation right here. The ways you do that, there's two ways. Have a polar protic solvent and have a tertiary carbon. It can go secondary, it can, but it prefers tertiary. So now I have this. Now this, a carbocation is planar, meaning it's flat. So this water nucleophile can come in from the top or the bottom. And because of this, you're going to have a racemic mixture. So racemic mixture means you have equal R and S. Okay, so 50% of this will make it R, 50%. This is looking at enantiomers. Versus SN2 will always make the opposite. So if you start with an R, you'll make an S. If you start with an S, you'll make an R. Okay, this will always make a mixture. So now this water comes in, makes a bond right there. These negative charge electrons will come here, positive charge. Now, why doesn't chlorine just come in here, you might ask? It's because water is your solvent and your nucleophile. There is so much water. 99% of this reaction is water. So since there's so much water, it's overwhelming that it has a much better chance than chlorine. Now though, water has a positive charge because it has too many bonds and electrons around it. It has really too many bonds, not electrons. And so it has a positive charge. So you see in the end here, it's going to lose a hydrogen. So there's two ways. You can either show chlorine coming over here and taking that hydrogen off, the electrons being left there, or you could show another water molecule because there's a lot of water molecules in here coming in and taking the hydrogen off. Okay, either way. And then you form your alcohol here. So that's SN1. So one thing happens is, so it's two steps. So don't think of 1 and 2 as in how many steps. Think how many things happen in your first step. This, in SN1, only the leaving group leaves. In SN2, the leaving group leaves and the nucleophile attacks. So here's just showing the nucleophile attacking the positive charge. Here's an energy diagram. Notice it happens in 2 steps. One hump, second hump. So first, the rate determining step, that's the one that needs the most energy. It's the slowest step. And that's when the leaving group leaves. So the leaving group leave is first step. The second step is when the nucleophile attacks. As I mentioned before, it prefers a tertiary versus a secondary because of the stability of the carbocation. And, you want a better leaving group. But, again, SN1 and SN2 both want good leaving groups. Here's the solvation. I told you that polar protic solvents work best because it's going to stabilize that carbocation. And that's very, very important. So, SN2 wants aprotic. SN1 wants protic. This is showing here that what I was trying to explain to your carbocation here, it's planar, it's flat. So you see here, the nucleophile can come in, say, from the top or from the bottom. It doesn't really matter. And you'll get a mix, a racemic mixture, which means if you had a stereocenter, say this was an S, you're going to get a mix of S and R as your product because it can come in on the same side as the leaving group or the opposite side. And that's about it. So I think that's where the videos leave off, but I want to make sure you really understand the difference between SN1 and SN2 there. I hope that helps.